Hey guys, what's up? I'm going to take dual nature of radiation and matter as fast as possible. I don't want to waste your guys' time. I know how valuable the time is, and I know how limited everyone has. How limited the time is. However, I would like to take this chapter because modern physics is one of the most important chapters in 12th physics, and it is having a lot of weightage, and hence the reason of why I started with taking modern physics. Well, considering the fact that if you revise every day and have a proper steady plan, you're not going to forget the concept, because you are most likely to you can recall, but it's going to be a hard job recalling, and you're going to waste a lot of time. So whatever, I don't want to waste my time yapping, and just go straight in the topic. So everyone take your notebook and write the chapter's name. Let me just try to get my short notes. If you don't know what I'm doing, I'm just taking short notes. This is where I write all the short notes and everything. Okay, so dual nature of radiation and matter, very easy chapter. I'll do it in 20 minutes. So first thing, there is three type of emission, like dual nature of radiation and matter. So first thing we're going to do is the process of it's a thing called it's a method where we are going to emit electrons from a metal surface, and that is known as electron emission. Okay, so write down, electron emission is a method of emitting electron from a metal surface, and there are three types of important I'm just going to tell all the theory part. You don't need to write it down in your note. You don't need to write all this thing down. It's not like you don't have time right now. You're just brushing up. I'm taking this chapter because I am thinking that you guys have already learned this chapter. So in brushing up the topic, there are three types. So we are mainly dealing, the first part we're dealing with electronic emission, where we are going to emit the electrons from a metal surface. There are three different ways to do it. One is thermonic emission. Thermonic emission is where we heat up the metal surface. We heat up the metal surface at a certain temperature, and the electrons will get emitted out. So in this area it's written that in this method the metal is heated to a sufficient temperature. One second guys, let me just take so here it says that the electron is heated up to sufficient temperature and the free electrons get emitted out, and that is your thermonic emission. Then we have field emission. So field emission is where you put a metal surface and you put electrical fields into this metal surface of the order 10 raised to 8 volt per meter, and then this will pull the electrons from the metal surface. And the third one is, which we are going to study, which is known as photoelectric emission. In this emission we radiate, we are basically incidenting into a metal surface a radiation of high frequency. Very important, high frequency, low wavelength. High frequency, low wavelength radiation is incident on a metal surface, and the electron gets jumped out, and this is your photoelectric emission. It's written here in this method, electromagnetic radiation. Electromagnetic radiation is about electrical field and magnetic field. It goes perpendicular to each other. So we are just saying electromagnetic radiation as radiation, UV radiation of suitable frequency. It's saying over here suitable frequency, but when we are talking it's going to be a high frequency, low wavelength. Just write this in your mind, high frequency, low wavelength of fall in the metal surface, and the electrons emitted out. That is your photoelectric effect, and that's all. And work function, what is the work function? It's denoted by lambda, and work function is basically the minimum amount of energy required. Work function means you have, it's written over here, the minimum energy required to eject electron from work function is nothing but it's a minimum amount of energy required to you have a metal surface over here, and you are incidenting a radiation, but electrons will not get emitted out until or unless you radiate energy which is above the work function. Get it? If you radiate the incident UV radiation above the work function, then only will the electrons get ejected out. There's actually a numerical which I have solved in my notebook, and it went like this. Okay, the question is like this. The question states that Yeah. One second. Okay, so the question is. The question is that a light of wavelength 412.5 nanometers incident in each of the following metal given. The first metal is sodium metal having work function 1.92 electron volt, and second is your potassium metal having a work function of 2.15 electron volt, and third is your calcium metal having work function of 3.20 electron volt, and the next second is your molybdenum metal, which is having 4.17 electron volt, and it is saying me which will show photoelectric effect. A light of wavelength is given. So for that, I'm going to calculate the energy because wavelength is given, work function is given. According to Einstein's photoelectric effect, E kinetic energy max is equals to E minus phi. Therefore, E is equals to kinetic energy plus phi. The light of wavelength work function sorry. You can use this formula to calculate your your energy, or else you can literally write E is equals to hc by lambda or h mu. Am I right? Yes, I am right. So if you don't know these two values, and if you know these two values, you can use these formula, or else you can directly use this formula. So over here the lambda value is given, so I'm going to do 6.6 into 10 raised to minus 34 joules, right? Into 3 into 10 raised to 8 by lambda is 412.5 into 10 raised to minus 9 into. So this is joule, right? If you multiply 1 electron volt is equal to 1.6 into 10 raised to minus 34 1 electron volt is equal to 1.6 into 10 raised to minus 34 joules. So you want to divide. So 6 minus 3 raised to 4, and you're gonna get this 3.01 electron volt. So my total energy I given, that is incident onto the metal surface, 3.01 electron volt, and the work functions are given over here. We know the minimum and we know maximum energy. We give 3.01. So anything which is above 3.01 won't work. Photoelectric effect won't work, right? Am I right? Because the work function here is a minimum energy required for photoelectric purpose. Here 1.92 will work. I have got my total energy is 3.01, 1.92 will work. 2.15 will work. But 3.20 won't work because 3.01 is my total energy, but my minimum energy I require is 3.20, but the actual energy I given incident to the metal surface is 3.01. So this won't work. And that is calcium won't work and molybdenum won't work. Only sodium and potassium will work. And that is how you find the minimum energy for your work function. And after work function is over, we'll discuss the Einstein's photoelectric effect. And I'm pretty sure everyone knows there's no need for further explanation. You just have to buy that equation. Einstein's photoelectric effect is that kinetic energy maximum is equals to kinetic energy maximum is equals to energy minus work function. Okay, and now we're going to do a relationship between work function and threshold frequency. Threshold frequency is basically the minimum. See, what I said, we need high frequency and low wavelength. A frequency means it should be always high. That means it can't go. See, this is the low, this is the minimum region, okay? So frequency should be always above this minimum area. If the frequency becomes low, it won't work. Photoelectric emission won't work. That's why in the beginning of this chapter I said that photoelectric effect means UV radiation incident should be of high frequency and low wavelength. That means frequency should be always above this paper. It should be always high frequency. If you go below this, If you go below this, it won't happen. So what is this paper? This paper is acting as a medium. So this is like the minimum frequency. If you this is the minimum frequency where photoelectric effect will occur. If you go above this, you are in safe region. But if you go below this, you are not in safe region, and that is called your threshold frequency. Threshold frequency is the minimum frequency required for photoelectric emission to occur, and that is denoted by phi is equals to h mu 0. Same for threshold wavelength. Wavelength will become the same thing as I said. As I said, we need low wavelength. Therefore, there is a maximum threshold wavelength. That means if you go above this point, then your photoelectric emission won't occur. You should always be below that. So that is your threshold wavelength, and that is over. Next is going to be your experimental setup. I mean, this is very occasionally asked for board exam. Just won't ask, but I'm just giving a theoretical concept of how it's going to become. Not make it so complicated. Okay. We are basically incidenting some some radiation. This is your emitter. This is your emitter. And emitters are usually some photosensitive metal like zinc, which will act as your cathode. You guys remember in electrochemistry we learned a small abbreviation. I always get confused in cathode and anode. Emitter is negative, so what is that? Loss no. Positive anode oxidation. Lone. Left oxidation anode. Yeah. Left oxidation anode. So left oxidation anode negative. Anode is negative. So which is anode and which is cathode? I'm getting confused, guys. 1 second. I'm not sure a particular retarding potential being not. Okay guys, we're not specifying which is an anode or cathode. So we are specifying this as C, which I assume that is supposed to be cathode, and this as A, which I assume it is be anode, but they're not specifically calling out in my notes or what. Okay, so emitter plate, so we have emitter plate C, which is always a photosensitive metal like zinc, and when we put radiations or UV radiations onto it, the plate C and A are enclosed by a glass tube. Okay, this is basically your so-called glass tube, ladies and gentlemen, and it is usually a transparent quartz window which allows UV radiation to pass through it. When UV radiations are incident on a when UV radiation is incident on a photosensitive emitter plate, electrons will be emitted out towards the collector plate, and this is your collector plate. So what happens, electrons get emitted towards the collector plate, and the potential difference between electrons, okay, the photoelectric is measured as okay, and this is what is actually happening. But however, if we increase the potential, I mean, if we pause, if in the sentence is saying that at some positive accelerating potential, that means when we increase the potential, or else we can say in simple terms as we're not like, basically what we're doing is on increasing the positive potential of A with respect to C, on increasing the positive potential of anode with respect to cathode, more and more, see, this is positive, this is negative, so more and more electrons are getting attracted. So more electrons are coming. So if you draw the graph between the positive potential and the photocurrent. What is photocurrent? The flow of photoelectrons produces photocurrent. And photocurrent, which is denoted by PI, photocurrent. Positive potential, when positive potential increases, the photocurrent increases. The photocurrent increases and then reaches a maximum photocurrent. So it won't go above this. It will always be stable like this. And this is known as the saturation current. Saturation current is nothing but when we put a positive potential in anode with respect to cathode, more electrons flow and therefore the photocurrent increases and reaches a maximum value which is known as saturation current. That's all. However, if I remove this and apply a negative potential, what will happen if I put a negative potential? Electrons will come. However, electrons don't like negative because electron itself is already negative. Why does it need more negative? So they will start repelling. And so they will start repelling, and then if I like, this will be negative, right? This will be positive potential. I put negative potential. So what happens is, the amount of electrons reaching the collector plate will decrease. However, if we apply negative potential to anode with respect to cathode, photoelectrons will decrease because of repulsion by A. And therefore photocurrent will obviously decrease. Photocurrent will decrease, and on further increasing the negative potential, it reaches a situation where no electron will reach the collector plate, and this region is known as stopping potential. So what is this region is known as stopping potential is when no current flows. Okay. So what is stopping potential? Is the minimum magnitude of the negative potential which is required to make the photocurrent photocurrent zero, or just to stop photocurrent is known as stopping potential. And the equation for stopping potential in this chapter is very simple, and it is a very easy way to get a stopping potential. Very easy way. So basically the equation given is EV naught is equal to kinetic energy mass. Okay, and why do I say it's very simple? Well, recently I got a question in my exam. I'm doing all this hard work. I just wrote exam today, 9 o'clock, and I just came home. And I just want to show you the question, like what question I got. Let me just quickly search it. There we go, we got it. This is my question paper which I wrote today for physics exam. I didn't study wave optics. Sue me, I don't care. But the question is, where is it? Let me try to find it. The question, this is your relation, right? The question given was, the stopping potential of a photocell in which electrons with maximum kinetic energy of 6 electron volt. So the stopping potential of a photocell so what is the stopping potential of a photocell in which electrons with a maximum kinetic energy of 6 electron volt are emitted? So here the kinetic energy is given as 6 electron volt. It says me to find the stopping potential. So EV0 is equal to 6 electron volt. So V0 is equal to 6 electron volt minus E. So V0 is equal to 6 volt. Easy as it. Easy as it. That's all. That was easy one. That was a relation. So that is basically what we call as a relationship between stopping potential and kinetic energy. Both are same, right? Okay, fine. Now we will do some graphs. These graphs are very important, and you can expect some question like this for board exam, because the board loves to give graph. Loves to give graph. What happens? Effect on intensity, right? The first point. Effect on increasing the intensity. When you increase the intensity, okay? Just imagine the picture of the photo cell which I wrote before. um, what is it called? Not photocell. It's called a experimental setup of photoelectric effect. Okay. So all I want to say is, before starting this chapter, there are some properties I wanted you guys to go through, and these are known as the laws of photoelectric effect. So the laws of photoelectric effect, there are 4 laws. I don't know why. The first law says that for a given frequency, yeah. The first law says that the number of photoelectrons emitted is directly proportional to intensity of the incident radiation. So basically, if you increase the intensity, number of photoelectrons increase, therefore resulting to increase in photo current. So intensity increases, photo current also increases. Easy. And the kinetic energy of photoelectron is directly proportional to the frequency. See, kinetic energy is always directly proportional to frequency and wavelength. Okay, it is independent. It is independent of intensity. Why do I say that it is independent of intensity? As I said, when intensity increases, photoelectron increases. What is happening with photoelectron is basically more photons are coming and hitting the metal surface. More photons are coming and hitting. But however, write this in your mind, underline it, very important. Even though I increase the intensity of the radiation, resulting in more photons, resulting in more photoelectrons, resulting in more photocurrents, the energy in each, listen to me, the energy in each photons will not be affected by increasing in intensity of the UV radiation. Why? Because it is the freaking law of photoelectric effect, and it says that the kinetic energy of photoelectron is directly proportional to frequency of incident radiation. That means if you increase the frequency, obviously kinetic energy will increase. That is seen in Einstein's photoelectric effect, which resulted to give a Nobel Peace Prize. However, E is equal to mc square, which is mass equivalence relation, did not give him the Nobel Peace Prize. But this equation is very important. That is kinetic energy max is equals to energy minus work function, and that gave him and kinetic energy max is directly proportional to frequency. However, it is independent of the intensity of the radiation. As we increase intensity of UV radiation, number of photons increase, therefore photoelectron increase, therefore photocurrent increase. But on increasing intensity, the energy on each photon does not increase. It remains same. That is E is equal to, what is the energy of each photon? E is equal to hc by lambda, or E is equal to h mu. Hence no change in kinetic energy. Therefore, when someone asks you to draw kinetic energy, this is kinetic energy and intensity graph, it's going to be stable. Which is the dependent and independent variable over here? Come on, tell me. This is a kindergarten question. I don't need to answer. Obviously, this is the independent variable and this is the dependent variable. And on increasing the intensity, the kinetic energy always remains constant because the energy is constant. But when we increase the intensity, number of photocurrent increases, therefore number of photocurrent increases. Okay, that is an important graph which I showed first over here. Next is very interesting graph. I'm combining all this together. This is the positive potential, negative potential, and this is your photocurrent. Okay. So obviously, on increasing the potential, what happens? Photocurrent increases and reaches to a maximum value called saturation current. But on decreasing, on increasing the negative potential, or the anode with respect to cathode, the number of photoelectrons reaching the collector plate will decrease, hence the photocurrent decreases. And on increasing this negative potential, the photocurrent decreases and reaches zero. And this minimum magnitude of this negative potential in which a photocurrent stops is known as stopping potential. And I said before, when you increase the intensity, the photocurrent also increases. Therefore, I have another one over here with I1, I2, and I have another one over here with I3. So here, if I ask you which is having maximum intensity, it should be I3 greater than I1 greater than I2. Because the intensity of I3 is greater, that's why it is having more photocurrent. However, intensity is independent on stopping potential. That means when you come over here, we are not looking about intensity. Even though this is highest intensity, that doesn't mean that it will have the least stopping potential or the more stopping potential. When it comes to stopping potential, the depending factor will be frequency. I want you guys to write it down. Very important. In the right hand side, intensity depending factor will be photocurrent. If the intensity value is greater, photocurrent value will be greater. However, in the left hand side, frequency will be the rate determining factor, and frequency, if it is less, stopping potential is less. If frequency is great, stopping potential is great. Assuming that everyone has equal frequency, they will all have a common stopping potential if they have equal frequency. Photocurrent increases with increasing accelerating potential of collector plate and reaches the maximum value called saturation current, which I already said. The stopping potential is same for the intensities I1, I2, I3. Thus, the stopping potential is independent on the intensity of the incident light. But the photoelectric current, saturation current increases the intensity. I said that. However, very important, stopping potential increases with increase in frequency of incident light. If I draw a vice versa graph, mu1, mu2, mu3. Yucky. Here intensity is common, that is why it is having a common photocurrent. However, in the left hand side, why am I saying left hand side? I am saying left hand side because it is left for you, it is right for me, but it's left for you guys. In the left hand side, it's actually, when I do like this is right, so when I do like this is left. Whatever, frequency, which is having higher frequency, obviously. This will be your frequency in decreasing order. So basically, this will have higher frequency because of high stopping potential. That's all in this area. Let me see how long the video has become. I can't see the time lapse. I don't know why. Got a question in my paper. It was like work functions in terms of parameters L, N, M. I never understood that shit. Okay, so I will just give you a brief overview. Kinetic energy max is equals to E minus phi This can be written as half mv square is equals to hc by lambda is equals to minus hc by lambda 0, or this can be written as h mu minus h mu 0. And then we can write kinetic energy as EV0 is equals to hc by lambda minus hc by lambda 0, or V0 is equals to hc by lambda 0 minus hc by lambda E minus hc by lambda 0 E. And there are different ways of writing this. And there's one way where we write V0 is equals to h mu by E minus h. But this is work function by E. And basically when we plot the graph, this gives the equation y is equals to mx plus c. So here m is your slope, therefore slope m is equals to h by E. And if you want to get the Planck's constant, you multiply the slope times E is equals to h. And work function, basically your y-intercept is the work function, right? Yeah, that's all. These are all important equations you got to know. And now let's go to the particle nature. We were doing particle nature the entire time. This is all Einstein's theory for the particle nature. Let's go to wave nature. That is where people like de Broglie. It's not de Broglie, man. I mean, you can pronounce it however you want to, but as a French scientist, you have to pronounce this guy's name in a French accent, in a French pronunciation, in a French manner, and he is called as de Broglie. De Broglie. Photoelectric effect and wave theory of light. Greater the intensity of incident radiation, greater will be the amplitude of the wave. When the amplitude of the wave increases, the energy density of the wave increases. That's how I am. Guys, all I have to say is some important equations. Lambda is equals to h by p, lambda is equals to h by mv, lambda is equals to in terms of kinetic energy 2km, check 2kme, I suppose. Woo, 2mk, yeah, 2km, it's all 2km, 2mk, and lambda is equals to h by. So this equation is important when we are dealing with anything which is moving. Kinetic energy charging when a charge is moving under potential difference, and that equation is 2mqv. However, if you have an electron, lambda equation can be redefined as 12.27 by v, and we will get the answer in ammeter. Did I just say ammeter? Armstrong, which is 10 raised to minus 10 meter. Yeah, that's all. And particle nature of light. For lighter frequency, all photons have same energy, which I said before. All photons have same energy, which is h mu, and momentum h mu by c, it's independent of intensity of light. Very important line. Photons are independent of intensity of light. That means the energies of photons independent of intensity of light. That means energy of the photons only changes on changing frequency. On changing frequency and lambda. High frequency, low lambda. Frequency increases, energy increases. Frequency lambda decreases, energy increases. Light have greater intensity, contains more number of photons. I said before, as intensity increases, photons level increases, but energy in each photon never increases. But the energy of photon is independent of intensity. Photons are electrically neutral and are not deflected by electrical or magnetic field. In photon particle collision, such as photon electron collision, the total energy of the total momentum are conserved. However, the number of photons may not be considered in a collision. Then we come dual nature of matter. De Broglie found that particles have both matter and wave nature. He wrote in his thesis statement it is known as de Broglie's hypothesis. Hypothesis, you write your thesis statement when you're doing some PhD or all those stuff, and in this thesis statement you come up with some, I don't know, you write some research you do, and then you come up with a final thing, and then you provide a lot of examples and this and that. But however, in de Broglie, when he wrote his thesis, he wrote a hypothesis. That means that he said that every matter you see in this world not have two natures, that is particle nature and wave nature. And he wrote some 50 lines about that, and he never provided an example. He just said that is basically how particles that he just said that particles have a dual nature. He just said that materials have a dual nature. That is, it has particle and a wave. And it is a hypothesis because he does not give an example. That's why it's called as hypothesis. And matter wave is the waves associated with matter particles are called matter wave, and de Broglie's wavelength. Yeah, those are the equations you have to by heart. That's all, guys. Dual nature of radiation matter is over.